Hello, I am the bus lead and my name is Ivan Jed. Now let's talk about the W bus or simply the bus. So if we zoom in here, you can see the 8 lines, right? That is our bus. So imagine you see these components: the program counter, register, ALU, the MAR, and the RAM. So these components are exchanging data. So now, without the bus, you need to connect each wires to different components. For example, the program counter to MAR, the MAR to the RAM. So, as you can imagine, it's very chaotic and very messy. So, to aid with that problem, we create the bus. So, the bus is basically the central, it's like a central highway in which the data flow. Yes, basically it. So if every component is connected to the bus, how should the component know when to input data and when to get data from the bus? So there's something like we call the tri-state buffer, or here we can actually see it here. Let's try to zoom out in the MAR. So as you can see, the buffer is what you see here, the triangle. So there are 3 states. One is the high impedance or the disconnected. Next is the output enable, and then lastly is the out. So that's it, 3 state: disconnected, out, and in. So for example, here in our MAR, you can see the in here sa ating MAR in. Yan, meaning the MAR is getting the values from the bus. And then if it's MAR out, the MAR is outputting values onto the bus. Now let's zoom out so we can see it clearly. Next, let's simulate a scenario. So let's say, for example, the program counter outputs data, or the address. So now let's say for example the address is 1. So it will output in the bus, and then the MAR will input. The MAR will receive the data. Let's say in our example 1, MAR will receive that data. Now, since MAR is basically a pointer to the RAM, right? So the program counter points to the MAR, and then the MAR points to the RAM. Now, the MAR will output data, which is 1, address 1. Then the RAM will receive that value, the address, and then the value of the RAM that is in that address 1, will be transferred to the instruction register, also to the through the bus. So next, so therefore we conclude that W bus, or simply the bus, is what makes stored program computer possible. So it is what makes SAP1, SAP2, and even this Benz Ether 8-bit computer possible. It reduces wiring complexity and allows dynamic data flow. And then without tri-state logic managing the W bus, this computer would simply short circuit. So basically that's the whole point of it. Uh, More efficient, less chaos, and less prone to short circuit.
Good day, sir. I'm Altea Bautista, and I'm assigned to explain the control sequencer and microcode lead. So my task is to analyze the ring counter, decode the microcode stored in the control ROMs, map the instruction set, and explain how these control signals execute our two programs, which is the infinite loop counter and the Fibonacci generator. The CPU uses a ring counter as a timing sequencer. It cycles through T0 to T4, where each T state activates specific control signals. These timing states break one instruction into micro operations. The fetch cycle takes two T states in this design. So at T0, the program counter outputs an address and loads it into the memory address register. Then at T1, RAM outputs the instruction and loads it into the instruction register while the program counter increments. After fetch, execution happens in T2 through T4 depending on opcode. Different instructions activate different control signals through microcode. The control signals are generated by two ROMs, namely ROM 1 and ROM 2. Their address inputs combine opcode, tstate, and flag bits, producing the microcode outputs. By analyzing the ROM address space, the CPU supports these opcodes. Conditional jumps like JC and JZ depend on the flag register. If carry or 0 is active, the jump control signal is enabled. Otherwise, the jump micro operation is skipped. So for program 1, the microcode repeatedly adds 1 to the accumulator and outputs the result. When overflow sets the carry flag, JC jumps back to the beginning. Here's what the memory looks like. So at address 0, we have 2F, at 1 E0, 270, 360, and F01. Okay, so we have here the instruction execution timeline on how this microcode executes program 1. So first we have add. This instruction loads the operand, performs allo addition, stores the result back in register A, and updates flags. Next we have out. Out transfers the accumulator to the output register, and then JC checks carry to reset after overflow. So the second program generates Fibonacci numbers by adding two stored values, displaying the sum, updating memory, and repeating until overflow causes reinitialization. So here's what the memory should look like. At address 0, we have 1C, address 1 2D, 2E0, 370, 44B, 51D, 64C, 71B, 84D, 960. So this program demonstrates more extensive use of load, add, store, output, and conditional jump instructions coordinated through the same sequencer and control room. So here is a simple memory flow diagram of the Fibonacci program. So in summary, the ring counter provides instruction timing, the control rooms generate micro-operations, and these control signals make both the infinite counter and Fibonacci generator possible.
Good day, sir, and I am Paul Wesley Gomez, and I am tasked with Role 3, which is the ALU and status lead and visuals. My task is to analyze how the arithmetic logic unit performs operations, how status flags are generated and latched, and how those flags support program behavior such as overflow detection and conditional jumps. So here we can see the ALU is located here and the ALU is the arithmetic core of the CPU. It performs addition and subtraction using these inputs, which is the A in and B in, and that is that serves as the register A and register B, and the outputs are indicated here, and it results back onto the bus, all over the output register, which is here. So for addition, the ALU receives value from register A and B, and it can generate a carry if overflow occurs. So we will be trying that one. So let's try 255 plus 1. FF. So let's try it. So here, as you can see, the overflow. So this test confirms overflow behavior. Adding 255 and 1 wraps the result to 0 while raising the carry flag. So the ALU also performs subtraction in the CPU. Subtraction is implemented through two's complement arithmetic. So let's try this one too. Here. So is subtraction X or base? The subtractor is built using XOR logic, which is this, for conditional bit inversion plus carry in for twos, rather than using a separate dedicated subtractor. So when it comes to plugs are stored in a plug register and updated only when the FI signal is asserted. This prevents plugs from changing unintentionally. And that is all. Thank you, sir. Also, for the program that we made, which is the infinite loop counter, The ALU plays a central role in it by continuously performing an addition operation. In each cycle, the value stored in the accumulator is sent to the ALU, where the constant value 1 is added to it. The result is then written back to the accumulator, effectively increasing the count step by step. The process repeats indefinitely, creating a counting sequence from 0 to 255. Once the maximum value of 255 is reached, the next addition causes an overflow. At this point, the result drops around back to 0 and the carry flag is set to 1. The carry flag is then used by the control unit to trigger a conditional jump instruction, specifically the JC or jump if carry. This causes the program to return to the beginning of the loop, restarting the counting process. This demonstrates how the ALU not only performs arithmetic operations but also works closely with status flags and control logic to enable automated and continuous program execution. Also, in the Fibonacci generator, the ALU performs repeated addition, but unlike the infinite counter which adds a constant value of 1, this program adds two changing values stored in registers. Initially, the system starts with two base values, typically 1 and 1. These values are fed into the ALU through register A and register B. The ALU adds them together, producing the next Fibonacci number. After each operation, the result is stored and the previous values are updated. One register takes the new result while the other shifts to hold the previous value. This allows the ALU to continuously generate the sequence by always adding the last two numbers. As the sequence grows, the values increase rapidly since the system is limited to 8 bits. Once the results exceeds 255, an overflow occurs. At that point, the carry flag is set to 1. The control unit detects this carry flag and executes a conditional jump instruction such as JC, which then resets the program back to the beginning. This allows the Fibonacci sequence to restart and run continuously.
Good day, sir. I'm Ian Benedict Untalan, and I'll be explaining the memory system of our 8-bit computer. My role focuses on how data is stored, accessed, and modified during execution. Also, my job for this video is to prove that RAM works read and write, MAR works for addressing, program mode works for manual input, STA write back works, and RAM doesn't fight the bus during fetch. So, our memory system consists of a 16-bit RAM and a 4-bit memory address register or MAR. The MAR holds the address of the memory location currently being accessed, while the RAM stores both instructions and data. So, during execution, the address is first loaded into the MAR from the bus. As you can see, it is being loaded. Then, the RAM uses that address to either output data onto the bus or accept data from the bus. This is the dip switch for controlling the address, and this is the dip switch for controlling the data. So our system supports a manual programming mode, meaning when program mode is enabled, the CPU is disconnected from the RAM, and so that we can directly input data using these two dip switch. To program data, first we need to enable auto tick enabled and click enable. So it is just continue running, as you can see. Now when we program, and then press right, it is stored in the RAM. See? Second address, the lights will turn off because this is a new data. Then press right, it will be stored in the RAM also. Second address, third, then lastly, and then when we are finished to input our data using our dip switches, we can just turn this off and then turn off the programming mode. I will just reset it, so as you can see, our 7 segment display starts running. We can adjust the tick speed so it moves faster. It will run until 255. Also, when program mode is disabled like this, the RAM is controlled entirely by the CPU. The MAR receives the address from the bus here, and control signals determine whether the RAM performs a read or write operation, like I showed you earlier. So, the most critical operation in the memory system is the store accumulator instruction, or STA. During STA execution, the accumulator places its value into the bus, and the RAM writes this value into the address currently stored in the MAR. So I will run a program that uses STA, like program 2. So I will program it. I just programmed the program 2 for our STA. The most critical operation in the memory system is the store accumulator instruction, or STA, which is here, register A. During STA execution, the accumulator places its value onto the bus, right here. Then, it transfers its value into the bus, then bus to RAM. So, the RAM writes this value into the address currently that is stored in MAR. This write operation only occurs during a specific T state when the write enable signal is active. As you can see in the RAM, the value is changing. Let's check the MAR. During fetch cycles, especially at T0 and T1, the RAM must not drive the bus. This is ensured using a tri-state buffer controlled by the RO signal. This prevents bus contention, ensuring that only one component controls the bus at a time. So going back at the program 1, in program 1, the RAM stores both instructions and constants such as value 1. As you can see. Now, the CPU repeatedly reads these values from memory to perform the counting operation. Going back in Program 2 demonstrates full memory interaction. The system reads two values of the memory, computes their sum, and then writes the result back into the memory using the STA instruction. As you can see, the value are changing because the program continuously updates memory locations to generate the Fibonacci sequence. So, as shown here, the RAM values are being updated dynamically during execution, confirming that both read and write operations are functioning correctly. In conclusion, the memory system successfully supports both manual programming and automated execution, with proper synchronization, controlled write-back operations, and safe bus interaction. So I have common questions here that can be asked, like when does RAM write? RAM write only when the write enabled signal is active during the STA instruction. Why use MAR? The MAR isolates the address from the bus, ensuring stable addressing during memory operations. What happens if RAM outputs during fetch? It would cause bus contention, which can corrupt the data or break execution. How do you switch between program and run mode? Using a multiplexer controlled by program mode that selects between manual input and CPU control.
Good day, my name is Ashley Magdalene B. Valera, and my role focuses on managing the execution sequence and the instruction decoding of our CPU. This includes the program counter and the instruction register. The program counter is a 4-bit register that stores the address of our current instruction. It supports two operations: normal increment when the clock enable is active, and jump loading when the J signal is asserted. This multiplexer here selects whether the PC continues sequential execution or jump to a new address from the bus. Our instruction register stores the 8-bit and instructions fetched from memory. It splits the instruction into two parts. Here's the splitter. Bits 7 to 4 represent the OP code sent to the control unit, and bits 3 to 0 represent the operand or memory address. The operand is only sent to the bus during execution phase using a tri-state buffer. This ensures there are no bus conflicts during the fetch time. Now I will demonstrate the jump instructions. During the execution, the jump signal becomes active, causing the program counter to load the operand instead of incrementing. As shown here, the program counter successfully redirects to the new address, confirming correct control flow execution. In program 2, I changed the RAM values in program 1. The RAM values means that 2F is load fetch, The E0 is jump control instruction. 70 is ALU operation or store. 60 is end program. And F equals to 1 is data stored at address F. And that means short execution flow. Get data from memory location F. It it results simple program, few steps, likely ends fast, and uses only one data value. While in program 2, there is a much longer program with looping and multiple operations. The step pattern currently is it loads values 1C and 2D, executes control, jump or branch likely, performs ALU operations, and uses multiple memory data values. This means it has multi-step computation, uses multiple memory addresses, includes loop or repeated operations, processes more data than program 1. The first RAM set represents a short and simple program with minimal instructions and limited data usage. It executes a direct sequence and halts quickly. While this program, the program 2, is more complex program, it uses multiple memory addresses and includes more operations such as arithmetic and control flow, making the execution longer and more dynamic. As the program counter increments or jumps based on control signals. These two programs demonstrate how instruction sequence changes CPU behavior significantly. Here is how it looks or how it runs.
Hello, my name is Ivan, the display and software lead. And my task here is to verify and check if our binary display is working perfectly. So, of course, before every program starts, we need to first upload our codes, which are here in our RAM, and then you can see this at our technical manual. So I'm not going to elaborate about the code further and focus on our simulation. And then we go back to our main, of course. So now let's start our simulation. So this program is about increment. So of course we start by 0 and then add 1, add 1, then add 1 until we reach the maximum values that we can reach. And then it is expected that after we reach the highest value, the program goes back to 0. And then do the same process all over again. So let's see if it works. So here we can see that it works perfectly fine. 5, 6, 7. Now let's make it faster so that we can reach its highest value faster. So of course, the highest value in an 8-bit binary is 255. Okay, let's see if it works. Okay. There. So there we saw that after reaching 255, it immediately goes back to 0. So that works perfectly, and then that's it. Let's move on to our second program. So next, we will simulate and verify and check the binary display for our program Fibonacci sequence. So of course, of course, earlier I've loaded the RAM with the opcodes. So as you can see here, so that we can move on for our simulation. So of course, let's exit the program mode. Let's enable the clock. Then let's simulate. So Fibonacci sequence is, okay, wait, 1 2, next it should be 3, after that it should be 5. So how does the Fibonacci sequence work? So it works by adding the last two numbers in the pattern. So as you can see, since we have 1 as our first number, there's nothing after it. So let's use the 0. 1 plus 0 equals 1. So now our last two numbers is 1 and 1. And then if we add that, it will be 2. Now the last two numbers are 1 and 2. 1 plus 2 equals 3. And then, sorry, 2 plus 3 equals 5. And then 5 plus 3 equals 8. So that's how the Fibonacci sequence works. And now let's talk about how does the binary display is achieved. So of course, our computer does not understand our digital data, or our digital display rather. So of course, it's just a combination of 1 and 0. It is in binary form. Now, as you can see, the binary display is just a combination of LEDs arranged in a certain way. You see, right? Now we convert the binary by using the decoder, or you may call it translator. In hardware, we use IC that is specific for the conversion of binary to digital display. So that's it for your software and display lead.